Section 2.4, the inverse of a linear transformation. This is where we are going to learn how to undo a transformation. So it's similar to inverse functions, but for matrices. So we're going to learn how to determine whether a matrix is invertible algebraically or through a geometric interpretation. We're going to find the inverse of a 2x2 matrix, which is something we did in pre-calc. And we're going to use the determinant to find the area of a parallelogram. So a function, that's just a reminder, y equals f of x, has an inverse if each output y has a unique input x. So that is called the horizontal line test sometimes, but it's simply the fact that if you pick a single value y, there's only one x such that f of x equals y. And we can, by extension, think similarly of linear transformation. A linear system ax equals y is invertible if for any vector y, for all vectors y, there's only a single x such that ax equals y. That is important because if we want to find the inverse, then by picking a vector y, I want to have only one choice of going back towards x. I don't want to have two x's that I can choose from. An n by n matrix is invertible if and only if the rank of A is n. If we look at ax equals y and think of it as a system of linear equations, we can see how this makes sense. We don't want to have free variables if we want a unique vector x such that ax equals y, and we certainly don't want it to be impossible either. So we need the rank of A to be equal to n. It might be worth going back to the propositions in section 1.3 where we saw these arguments B and C in the exercises that we are doing now with invertible matrices. It's always square matrices, so n is equal to m. So we want the system to be consistent and to have at most one solution in order to have one unique solution. So the rank has to be equal to to n and to m, which is the same. If the rank is n, that automatically means that RRE f of A is In. The system ax equals 0 has x equals 0 as a solution. This is always the case. It's something that we need to realize. It's straightforward. Here's a simple example with a vector x that is 0, 0, 0. Whatever the matrix is, if we choose x equals 0, then we will always get an output of 0. So if we're trying to solve ax equals 0, then this is always a solution, of course. Which is also a good way it's also a good first step for checking if a question is this transformation linear? One of the first things you can do is to try to plug in x equals 0 and see that you indeed get 0 as an output. If it's not, then the transformation is not linear. For example, with lines in the plane y equals ax plus b, if b is not 0, then we see that this is not a linear transformation in the sense of linear algebra. Let's think about that also geometrically. If we go back to section 2.2 and the transformations that we saw, geometric transformations in the plane, for example, let's take a scaling matrix. So that's a matrix that would zoom every vector. The vector, let's say we scale by 3, so the vector 2, 1 then is transformed to the vector 6, 3. When you think of the geometry of a scaling, the only vector such that ax is going to be equal to 0 is 0 itself. Any other vector will be zoomed and is certainly not going to become 0. And we can see how there's only one solution to a scaling, but we could also think, let's think about a reflection across a line. If you think of ax equals y and you pick a certain vector y, then there is only one x such that the reflection across that line is going to give you the y that you are looking for. And for a reflection as well, the only vector that is going to be reflected to 0 is 0 itself. So it's always good to juggle between these algebraic expressions that we see and the meaning that they can have geometrically. If A is invertible, this is the only solution. And that comes directly from what was written above, that if A is invertible, then there is only one x that is such that ax equals y. So there should be only one x such that ax equals 0. And we know which one it is. It's x equals 0. If A is not invertible, then there are infinitely many solutions to ax equals 0. So here again, if A is not invertible, it would mean the rank is less than n, and there's either infinitely many or no solution, but we know there's at least one, so that means automatically there's infinitely many solutions. Note that if we are aware of one vector such that AV equals 0, so V would not be the 0 vector. If we know of one, then we know of infinitely many automatically, because A of 2V is equal to 2A of V. So if A of V is 0, then that is equal to 0. So if a certain vector is such that AV equals 0, then any factor of that vector is also going to go to 0. Now about inverses. A inverse, A with a -1 is called the inverse of A. We say just A inverse, and if A is has an inverse, it is said that A is invertible. If not, A is non-invertible. To check that a certain matrix is an inverse of another one, you would do A times A inverse and check that you get the identity matrix. You can equivalently do A inverse times A, of course, and you would also get the identity matrix. You only need to do one of these. There's some extraordinary situations where maybe we would need to check both, but certainly not in this course. So if we need to check that these two matrices are inverses of each other, we just multiply them and see, oh yes, I get 1, 0, 0, 1. But how do we find the inverse of a matrix? Well, there's a strategy that we can use that works for any order of matrices, provided they are square matrices, and it kind of looks like how we would find the inverse of a number. So if we're looking for the inverse of 7, we can write 7 on the left side, the identity on the right side, and then do stuff on both sides until we get 1 on the left. So here we would divide by 7, so we would get 1. And on the other side, we would get 1 over 7, which obviously is the inverse of 7. We can do something similar to find the inverse of any matrix. We can write the matrix, we'll see this example here, alongside the identity matrix of the same order, so a 3 by 3 identity matrix, which will look like this. And then, by going through a proper elementary row operations, we are going to try to bring the identity matrix to the left side, and then what will be on the right side will be the inverse matrix. So let's see this example. There's multiple steps. The first step here, as usual, is to bring zeros in these two spots, and so on, and so on, and so on. It's a little bit long, but in the end, we've managed to have the identity matrix on the left, and so what's left on the right is the inverse of the original matrix. If we gave names to these variables here, we could say column 1 is x's, y's, z's, and then here a's, b's, and c's. You can say that here we have a, b, c in terms of x, y, z. And after going through this entire process here, we have x, y, z in terms of ABC. So we do manage to kind of undo what we had. It's like in the original exercise in this chapter about coding coordinates. So we've managed to find an algorithm to uncode these coordinates. But of course, for 2x2 matrices, we have a formula that we know since pre-calculus. So the inverse of A is 1 over AD minus BC times D negative C negative BA. And this AD minus BC is called the determinant of the 2x2 matrix. So here's the first example, finding the inverse of 3625. And in some cases, we will see that the determinant is 0. 3 times negative 4 minus negative 2 times 6. So that means matrix A here is not invertible. For what values of k is this matrix here invertible? So we want to find the determinant and we want to avoid the determinant being 0. So as we expand and factorize again, we find that the determinant of A is equal to k minus 5 times k plus 1. So k needs to be anything except 5 and negative 1. It should be written negative 1 there. If A and B are invertible matrices, then AB is invertible too, and the inverse of AB is B inverse times A inverse. Notice how the order switched. We can check that this works, because if AB inverse, we should have parentheses here to be clear, if it is the, well, we know it's the inverse because we just wrote it, so this has to be equal to I, and if we use this formula, we get AB times B inverse times A inverse, and now B times B inverse is equal to I, and then we get A times A inverse, which is indeed equal to I. Geometrically, we can think about a few of the things we saw today, and let's start with this. If we think of A and B as two transformations, so first we have a vector x and we apply transformation B, and then we apply transformation A. If we want to find the inverse of that, then first we need to inverse A, and then we need to inverse B. So that explains why the order is switched. Lastly, geometric interpretation of the determinant of a 2x2 matrix. If you take the determinant of a 2x2 matrix that is built with vectors v and w, and you take the absolute value of that determinant, this gives the area of the parallelogram spanned by the two vectors v and w. It has a small sub-application, and that is that if the determinant of A is 0, then the two vectors are parallel, because the parallelogram spanned by v and w would have no area, and the only way this happens is if these two vectors are parallel. Or, well, it's not an or, it's included if v or w are 0 themselves, but that counts as parallel to any other vector.